Okay, good morning, everybody, or good evening, or good night, depending on where you are. This is Alberto Troccoli from the European Climatic Energy Mixes project here in Norwich, UK. And we're going to present to you a webinar called Discover the C3S ECEM Climate Data for the European Energy Sector. We'll explain in a minute all these acronyms, particularly C3S, an important one. But you'll see also the contributions from the 6 partners in the project highlighted at the top of the presentation. So thank you very much for joining us today. And let me say a few words about the project first before I hand over to the speakers. We have a great lineup, and I don't want to take too much time, but I want to tell you a bit about our project as an overview. So the European Climatic Energy Mixes ECEM is a part of the Copernicus Climate Change Service project or program, which is developing in close collaboration with the energy sector a demonstrator to assess how well different energy supply mixes in Europe will meet demand over different time horizons, focusing on the role climate has on these mixes. So I won't go into the detail, but I just want to show you a little bit the complexity of the project. And there are various aspects, but today we are going to focus on this upper left corner of the graph, which is the climate variables. Other webinars then will look at energy variables and also other aspects, particularly the demonstrator. We've already done one last month, and there'll be another one on the demonstrator. But let's focus on the climate variables for today. You see that there are several variables, and these have been chosen because they're relevant to the energy sectors, as we will see and listen in a minute. But let me tell you about the lineup of the webinar, because we got, as I said, a great lineup with Professor Phil Jones to start the discussions on the development of climate variables for the historic period within ECEM. And then we'll go to Dr. Phil Bett from the Met Office, who will tell us about what's been done in terms of seasonal forecasting for the energy sector. And then finally, Dr. Claire Goodis from the University of East Anglia again will talk about the development and visualization of climate projections. So we have these 3 timescales: historic period first, seasonal forecasting second, and climate projections. So we cover the whole spectrum of climate information. And then we'll have a session on question and answer at the end. And as I said, my name is Alberto Troccoli. I'll be chairing this webinar, as you can tell. The house rules are the following. So there are 3 presentations, as I said, with a question and answer. You can type your questions on the panel that you see on your screen. And although other people can't see the questions, I will be able to see them, and I will also copy them on this PowerPoint presentation, so everybody will see them. We'll read them out, and then the speakers can respond to them. And feel free to also highlight who of the speakers you would like to address the question to, or leave it open if you don't want to do that. So the webinar is recorded, and it will be available online, as all the other webinars that we've run so far. So you can, I'll provide the website later at the end, and you can go and look at the previous webinars, as well as a lot of other information available through our website. So I'm going to hand over to the first speaker, Professor Phil Jones, and enjoy the webinar. So over to you, Phil, please.
Okay, good morning, everyone. I hope my screen is now up. I'll assume it is, as no one said anything. So I'm going to be talking about the historic period. So we're looking at the period from 1979 to the present. and I'll briefly go over the climate variables that we've developed within Work Package 2 of the ECEM project. And we're looking at era interim reanalysis data from 1979 to the present, and we're adjusting that according to some observational data sets. And I want to look at what these adjustments are and where they're large and where they're small, and discuss some of the issues with those for some of the variables. And at the end, towards the end, I'll go on to how we compare these with some different real-world data sets and the issue of land-ocean masks in calculating some of the national averages. So what we're doing is we're assessing the quality of era interim by comparison to gridded observational data over land areas for various variables. I'll show you those variables lists in a minute. But the variables are mostly those relevant to renewable energy, so radiation, sunshine, and wind, and also precipitation influences hydroelectric power. And we're also looking at temperature and relative humidity because that influences demand. Now, era interim, despite being probably the best reanalysis, isn't perfect, but we can assess how good it is and when and where it's good in comparison to these gridded observational data sets. And improving it is the term we use for this is bias adjustment. So here's the variables, as I mentioned, air temperature, and we're looking at the mean, the maximum, and the minimum temperature, and nominally at 2 meters above the ground. And in precipitation, solar radiation, wind speed at 10 meters, and we also calculate wind speed at 100 meters with a formula, and also relative humidity, which uses air temperature and also dew point temperature. Now we're looking at era interim here, but we know that the European Centre for Medium Range Weather Forecasting is going to produce a new reanalysis very soon. There's a few years available now. This is called ERA 5. It will be complete by about 2019 for the same period, 1979 to the then new present. They're going to calculate wind speed at 100 meters directly. There'll be improved spatial resolution. It'll be hourly. And although it ought to be better than era interim, it's not going to ingest much more data. So it may also need bias adjusting. And ERA 5 will also provide ensembles, which give you a measure of uncertainty as well. So what we've done in the project here, and I've got one paper there in Earth System Science Data, we've tried to compare the ERA interim with station data sets, and all the details are in this paper. And bias adjustment was introduced to for global climate models and regional climate models, and these are projections of for the future. And the biases for these sorts of models tend to be larger compared to observations done for reanalysis. So, but we're applying the same types of techniques that have been developed for many years to bias adjust climate model output. And our approach, which is described in this paper, is distributional in nature, where we compare the distributions from era interim and the observations, and the distributions are different for different variables. So for wind speed, we use the Weibull distribution. For air temperature, the normal distribution, gamma distribution for dew point depression, a gamma distribution for precipitation. For solar irradiance, we're using the direct measure from satellite data to bias adjust era interim there, as there are very few direct observations across Europe, very few sites with long records. Now, the observational data we're looking at for wind speed and dew point depression, we're using something called the Hadley Centre ISD dataset, which is basically synoptic data every 6 hours, which has been quality assessed by the Hadley Centre, part of the UK Met Office. There's a Dutch Met Service data called EOBS for gridding temperature and precipitation data across Europe on daily timescale, and we use that for air temperature and precipitation. And for solar irradiance, we're using this HelioClim data set, which is available from the mid-1980s to the present. And as I said, there's more details in this paper, which is open access, and anyone can download. And you can also, through the links there, get to the data themselves as well. Now, one thing in this paper and in this project, we've tried to look at whether bias adjustment is worth doing. And one way of assessing this is to look at other aspects of the project where we develop transfer functions to take weather data and to assess how much renewable energy can be produced or how much hydropower, and issues like demand. So if one way of assessing the quality and what we're doing, whether it's worth doing, is to use unadjusted reanalysis data and then see if the bias adjustments make any difference to the simulations of energy and some of the energy variables we've got. Bias adjustment comes in a number of forms in the scientific literature, and one of the issues that's discussed a lot is whether you need to bias adjust. You can bias adjust variables independently of each other. So obviously, variables like temperature and sunshine and radiation are related. So can you do one without doing the other? Well, in the project, we've looked at this, and we've got one paper here which looks at multivariate bias adjustments. Generally, this is quite difficult to do for more than 2 variables. So even if you wanted to bias adjust 3, it would be quite difficult, and it's quite complex. And so at this stage, we've just done independent bias adjustment, independent for each variable. So there's no dependence between temperature and rainfall, or wind speed and solar radiation. Now, we've got these real-world data sets that I mentioned in one of the earlier slides. And we've also been looking at some other real-world data sets that are well used in the literature, where people have taken observational data and produced gridded products. And one of these is a data set called WFDEI. And this stands for the Watch Forcing Data Applied to Era Interim. Now, when you take any sorts of data like this, it's important to know something about their quality and how they've been put together. In particular, how someone has gone about taking irregularly spaced station data and put it on a grid, because a lot of the data sets and the reanalysis are on grids, and how that gridding is done can impact the results, and it can influence the quality of the data, particularly when you have very few stations in some regions and many stations in other regions. Anyway, with this WFDEI is based on Era Interim, but it's been adjusted to some observational data sets, one that we developed a long time ago called CRU-TS, which is updated regularly, and also the Global Precipitation Climatology Center for their precipitation data set. This is a Deutsche Wetterdienst product. But they don't adjust wind speed because there isn't a good gridded data set with which to compare. And they also don't adjust solar radiation. So I want to highlight here some of the issues when you do this comparison and how much you're bias adjusting the data sets. So here for wind speed, we have 2 plots. And they're for the period 1979 to 2016 on the left. This is the unadjusted Era Interim versus minus our adjustment. So this is how much we are adjusting Era Interim. And you can see here with the scales, we're decreasing the wind speed in some parts of Europe, particularly around the coastlines, and we're increasing it in other parts. So it's not just a sort of uniform change. It's very dependent on the distribution of the stations as to where the data is, and also how some of those station data has influenced Era Interim initially in terms of the input data that's ingested to produce the product. But you can also see on the right, for a similar time period, how the WFDEI dataset compares with our adjusted Era Interim. So you can see that there are somewhat large differences, particularly around coastal regions of Scandinavia and in the Mediterranean. And this is partly due to the fact that a lot of the observations are much larger around coastlines where wind speeds are higher compared to what ERA interim suggests. So these discussed a lot of these differences. They've been found by another project, one of the C3S projects called Climate for Energy. And although WFDEI is not adjusting ERA interim, there are differences that we were surprised to find, and a lot of these relate to the definition of the land-sea boundaries and the masks around countries. So some masks might omit islands, might omit some coastal areas around parts of Europe, particularly where you've got a lot of coastlines like Italy and Greece and the United Kingdom and Ireland, whereas other data sets include many more coastal squares and island squares. And for wind, whether that inclusion or not can have an impact on the wind speed data, particularly for countries where the wind speeds tend to be lower, maybe in Mediterranean compared to more areas of Northern Europe. It would be good if there was a gridded wind speed data set, and another C3S project called SURFOBS is going to look at this, but it might be several years before they've got together enough data from across Europe in order to produce one. So these are just plots of the coverage of the wind speed data that we've been using, and you can see that there are gaps. So there are many more stations in some parts of Europe and less stations in other parts. And there tends to be more stations around coasts than interior parts of some countries as well. And getting access to more data is one of the crucial aspects here, and this other project is going to have quite a hard task to get detailed station data in some parts of Europe. This is looking at the other two major variables here, temperature now, and we'll come to precipitation in a minute. So on the left you have the unadjusted ERA versus our adjustments to ERA for T mean, and you can see here that most of the adjustments are relatively small, particularly over more lowland parts of Europe. The adjustments tend to be higher around mountainous regions, and particularly in regions where you're near coastlines in southern Europe. And you can see the same thing on the right with the WFDEI comparisons with unadjusted ERA. So these are their adjustments effectively, and you can see that they're making similar adjustments. WFDEI includes an additional component which we don't, which is an elevation component. Obviously temperatures are higher when you're at low elevations, and they reduce as you go up mountains. As you can see, these effects are largest around mountainous regions again, but they're also affected by the coastlines as well. And this is the same thing for precipitation. Again, the biggest differences are in mountainous regions where the precipitation tends to be higher. And during this work, we've also produced a lot of these data into averages for countries across Europe and for clusters, which Claire will talk about later in the third of these talks. So the largest effects are for wind speed. It's partly due to the station network. The effects also appear larger for countries with long coastlines, particularly Italy and Greece, and the differences in Northern Europe are smaller. And for temperature and precipitation, differences with this other data set are mostly in mountainous regions and relate to their accounting for elevation. So a lot of this data is available, and it's going to be available at the Climate Data Store eventually. It's available now at the location given in the paper that I talked about, and it's probably essential that we look at this again when the new reanalysis comes out. So here's some of the discussion points, and I'll stop there as I can see Alberto asking me to stop. So thank you very much for listening.
Thank you very much, Phil. And I will now move to the next presentation, and we'll come back to you with questions at the end. But that was a very informative presentation. Thank you, Phil. We're going now to another Phil Bett from the Met Office, who is going to tell us about the seasonal forecast products developed under ECEM. Thank you. Over to you, Phil.
Yeah, hi, thanks, Alberto. As Alberto said, I'm Phil Bett. I work at the Met Office Hadley Centre in the UK, and I'm going to be talking about the stuff we're doing around seasonal forecasting for the energy sector in ECEM. So just so that we're all on the same page to start with, I'll define what I mean by seasonal forecasting or seasonal climate prediction. We're talking about forecasting ahead for several months, for example, a 3-month season, with a lead time of several weeks, for example, about a month. So, for example, you might talk about forecasting for the December, January, February period, winter, from initialized it at the start of November. So obviously traditional weather forecasts lose their predictability after about 10 days, just because the atmosphere is naturally very chaotic. So how we work, how seasonal forecasts work, is because some of the climate system components change slower than the atmosphere does. So things like the oceans, sea ice, soil moisture all change much more slowly. So, for example, you can think of it like the ocean is still predictable even when the atmosphere isn't, and we can predict how the atmosphere might then respond to the oceans. So this means we have to use a coupled climate model for seasonal forecasting. So we have a model of the atmosphere, a land surface model, an ocean model, and a sea ice model all linked together. And then these are initialized with current observations, and then we run it forward to try and forecast the climate for the coming season. Because these climate drivers are large-scale phenomena across the globe, and this means that our forecasts are only going to be skillful over fairly large areas. So thinking about Europe, we're talking about areas about the size of Spain or Germany or Britain or Poland, that sort of size. And they're probabilistic. So it's important, I don't want to labour the point too much, but it's important that we don't think of seasonal forecasting like extended weather forecasts. It's not just like a normal weather forecast, but with a really long lead time. So obviously we can't predict the weather on the middle of January from the start of November, but we can, as long as the skill, we can talk about whether the winter period is likely to be colder or warmer than normal. So this means that seasonal forecasts are really useful for different types of decisions, like longer-term risk-based planning than a weather forecast. And you'd use it always as part of a decision-making chain, along with the monthly or weekly or daily forecasts you get from your normal weather service. And so what are we doing in ECEM around seasonal forecasting? What we want to do is to demonstrate the use of seasonal forecast data from Copernicus Climate Change Service for the energy sector. And this, we obviously want to link in with the data sets that are produced elsewhere in the project, such as what Phil Jones has just talked about. But before we can provide forecasts, we really need to assess the skill of the forecasting systems. And the important thing to consider is that the skill will depend on the variable in question and the model used and the region and the season being investigated. It's not, you don't just get one number out of this sort of thing. So what am I doing? There's two different bits of work that I'm working on. This first stage was assessing the skill of the climate variables like temperature and wind speed that are relevant to the energy sector. That data is now on the demonstrator, and we've got full results in a report associated with that. A final update to that is coming end of October, early November. And after that, we move on to looking at the skill of different methods of forecasting energy variables themselves, such as energy demand, wind power, and so on, in select countries. And we'll be finishing that by the end of December 2017. There's also additional work on seasonal forecasting going on in the case studies work that's led by Emma Suckling at University of Reading. This was talked about in the previous webinar. So seasonal forecast skill is quite a large and complex area of statistics, and I don't want to go into it in a huge amount of detail. It's just important that we sort of understand that the uncertainty in a single forecast and the skill of the forecast system are related, but they're not really the same thing. There's lots of different ways of measuring skill. There's lots of related quantities like reliability and resolution, sharpness and bias, and many others, and so on. So we assess the skill of the forecast system. We estimate it from a series of reforecasts over the historical period, which we call hindcasts. We compare them to observations over the period. So you can see this in this little sketch graph here. So for example, this is, say, something like temperature along the y-axis and time across horizontally. So you have the forecast with its uncertainty there drawn on the end. But for these historical years, you can see you've got a reforecast for each year. So each of these hindcast years, it's got its own uncertainty. And there's some relationship with the observations. That we use these hindcast points to sort of sample statistically. And you can see in some years, the hindcast will do really well, and some years it'll do really badly. And the skill is some statistical measure of that overall. Of course, these hindcast data sets are going to be limited. You can see just from that diagram that if you have fewer years, you can't sample the skill of the system quite as well. And the number of realizations in the forecast ensembles also affects it, which means these skill estimates themselves are also going to be uncertain. Added to this, the actual real forecasts and the operational systems are often produced using a slightly different system to the hindcast. As you put a lot of the computational effort into the forecast system, so often the skill estimates we get from the hindcast will tend to be an underestimate of the actual skill of the system. So for ECEM, the way we're assessing the system is we're looking over a range of different models and parameters. So, for example, we're looking at the three latest seasonal forecasting systems from ECMWF, Meteo France, and the UK Met Office, which are sort of summarised in this table. So you can see they've got all got a fairly similar spatial resolution. They all use slightly different or very different climate models. Because these are coupled systems, they'll often have similarities, but they're all run differently. Spatial resolution is about the same. Their hindcast periods are all slightly different. You've got quite a long hindcast in ECMWF and slightly short ones in Meteo France and Met Office. The size of the ensembles in the hindcasts are different, and the forecast ensemble sizes are also different. So with variation there, I'm going to be comparing our results against both ERA interim itself and our ECEM bias-adjusted reanalysis that Phil Jones just talked about. I'm going to be looking in 2 different seasons over 6 different variables here, so wind speed, temperature, humidity, precipitation, irradiance, and air pressure. And we're looking at a range of different statistics as well. So we'll look at gridded maps of correlations, so I'll show some of these in a minute, and then go on to country average statistics, so time series, and more complicated probabilistic scores as well. So you can see this is quite a lot of data to be crunching through here, and quite a lot of results. So I'm just going to walk through an example just to sort of show how the process goes. So focusing on summer temperatures here. So start with looking at maps of correlation skill, so the correlation of the different hindcasts against ERA interim. So here are our 3 hindcast models from ECMWF, Meteo France, and the Met Office for summer temperatures. You can see immediately that skill isn't universal. There's quite a lot of variation between the different models and geographically as well. Although in this case we can see that there's some common signals across the models, particularly Southeastern Europe and the Eastern Mediterranean. We get good skill in all these 3 cases. So I've just drawn a yellow contour, you can hopefully just see that, around areas where the skill is significant, as in significantly different to 0. In all the other areas, it's statistically indistinguishable from 0, which doesn't mean there's no skill, but it means that we haven't got enough samples, certainly, to be able to measure the skill. So we shouldn't really believe numbers outside those areas. So the next step, from looking against ERA interim, we then look against the ECEM bias-adjusted reanalysis data. And the good news is that when you look at these seasonal timescales, actually the correlation doesn't change much, at least for temperature. That's very clear. So if I just flick between them, you can see, although we go from the full global gridded data to the land-only data we're using for ECEM, the actual gridded data points don't change much. So that's reassuring. And then we can aggregate it into countries. So here we're looking at the skill of the country average time series. And sure enough, we get similar results to what we saw with the gridded data. So we've got this common area of skill in southeastern Europe, and then for ECMWF, you've got a few more countries there as well. So, I've masked out the areas here, I've scribbled them out where the skill isn't significantly different to 0, so we can focus on the areas where we think we've got significant skill. And it's important that we take care with these country average data. So you can see that a lot of countries where we seem to have significant skill, the countries are actually very small, especially compared to the gridded data. So if I flick back to there, you can see the size of the grid cells is quite large compared to the size of the countries. So we want to take some of these with a little bit of care and caution. But we'll move on. We'll take the example of Romania here, as that's got consistently good skill across all 3 models. So we'll pick on Romania skill for summer temperatures. We'll show this as a time series. So there's our 3 models again. So in all of these we have significant correlation skill. So I've got the 95% confidence interval here next to the correlation R. And so you can see that actually there's quite a noticeable trend there in the observations in black. You can see it easiest in this top plot against the ECEMWF system. And so we know that the trend is going to be definitely a contributor to the positive skill that we see in all these 3 cases. It's not the only source of skill though. We do see skill just in the inter-annual variability. And a part of the reason the ECEMWF system definitely gets quite good skill here is because it's got the longer hindcast, so it can sample the trend a lot better. So as I mentioned, we also look at these more complicated probabilistic measures of skill. So this is just focusing on the ECEMWF system here. Here's reliability and sharpness diagrams for Romanian temperatures, and we get a significant Bryce skill score there. And a rock diagram as well, with a significant rock skill score. So both of those look good. I don't want to go into the details of how those are calculated or what they mean, but because these 2 are probabilistic more explicitly, it takes a lot more effort for the system to get the significant skill score here, because we're dividing up the skill into a lot more samples. So if having a correlation skill is good, and if you can get more skill scores to be significant as well, that's even better. So how's this data then shown in the ECEM demonstrator? So here's a screen grab of the demonstrator. So we have seasonal forecasting, climate data for air temperature selected from the ECMWF system 4, showing the correlation in the summer. So this is exactly the same data as I showed a few slides back with the country average, the correlations of the country average data. So again, we have masked out the areas where there isn't significant skill. So there's a tick box here to highlight that. And of course, you can pick on a country. So there's Romania coming up with its 0.66 skill correlation again, and you can plot that as a time series. So this is just showing that we have the same data now available on the demonstrator. So these are we have a lot of this data. So it's important to show that you would get quite a wide variety of results. So here I'm just going to show a whole range of results for different seasons. So focusing just on the summer and the correlation scores. So there are 3 models, and this is what we've seen already for temperature. So we extend this to the 4 other variables: wind speed, precipitation, irradiance, and humidity, and show what their correlation skill maps look like. So there they all are. So you can see immediately there's quite a lot of diversity and not a huge amount of areas with significant skill. So you have to be very selective when you're picking out where you might have some skill. There's some areas here with relative humidity that might be okay. You see some areas here in irradiance. Spain might be okay there. In the Met Office system, the precipitation in Spain might be okay, and irradiance. So you can see there might be some areas of promising skill, but overall, the message is you've got to be very selective to find areas of skill. And this is for the summer. If I move on to the winter, things start to look a little bit better actually. So looking at the same sort of thing here, the correlation map. So here's ECMWF temperature. You don't get a strong signal from the trend in this case, We've got quite a few countries here which look promising, and similarly in the Meteor France model, we've got some good skill here across northern Central Europe, and for the wind speeds as well. And a few more in some of the other variables. Yes, there's some good skill for irradiance, perhaps. The Met Office Glossy 5 system, and the final release of its new hindcast for this year is produced on a rolling basis, so we'll have that available in November 2017, so that'll be coming up. And obviously we've published various papers at the Met Office using the previous hindcasts, showing that we've got some good skill in DJF, especially around things related to the North Atlantic oscillation, so for example wind speed and temperature. So hopefully we'll be able to see those again. So we can summarize this at a country level as well. We have these tables that we've produced where you have all the different variables and the different models, and looking at how many skill scores we get significant for each country. So this is summer again, this is JJA. So this is where we don't have a huge amount of skill. There's a few areas for temperature. So where we've got, this is Hungary here in the middle, and Romania we showed earlier, and Bulgaria, that's sort of southeastern Europe. And here in winter, summarize it, you can see just immediately there's a few more countries over a few more variables where we get significant skill. Overall, we can say that it's very diverse across the different models. So just to sum up everything, seasonal forecasting uses global climate models to predict the climate of the coming 3-month season, with a lead time of about 1 month. And the skill comes from slowly varying components of the global climate system. The uncertainty means that we forecast probabilities of average seasonal conditions. And we use hindcasts of the historical period to estimate the skill of the forecast systems, but the limited size of the hindcasts means that these estimates are uncertain. And what we've seen here is that the skill in Europe is very diverse across different models, variables and seasons. And of course it's an open question how skillful you need a seasonal forecast to be before it's useful. So these initial estimates of skill are provided in the ECEM demonstrator now, and they provide, I think, a good starting point when considering how useful a seasonal forecast could be. So thank you for listening, and that's what I've got there. I'll hand back to Alberto.
Excellent. Thank you very much, Bill. That was really a good overview of the results you achieved, and there are so many with the seasonal forecasting. And I'm sure people will have questions, so I encourage everybody to type your questions in the box there, and we'll come back to you after the talk by Claire Goodis now, that who's going to talk to us about the projections results produced in ECEM. Thank you very much. Over to you, Claire, please.
Okay, thank you, Alberto, and good morning or good afternoon, evening, everybody. So, yeah, I'm going to wrap up this morning by talking about the development and visualization of climate projections for ECEM. So, Phil Bett has just been talking to us about seasonal forecasts and talking about prediction and predictability. And this information is important for the energy sector for making decisions in the shorter term relating to the balance of supply and demand, for example. But in ECEM we also provide climate projections out to the end of the current century, and the reason for that is to support sort of longer term decision making, perhaps investment in major infrastructure, and taking the longer term perspective. So as well as the types of decision making that the different information may be used for, the nature of seasonal forecasts and climate projections are somewhat different, and that's alluded to in this diagram here. So as Phil just told us, for seasonal forecasting, it's what we call an initial value problem. The starting point of the climate system is very important. For climate projections, it's what we call a force boundary condition problem. And I'll talk a bit more about that and explain what I mean by that. But first of all, let's start out with some definitions. So I'm going to be talking about scenarios and projections. And this is quite a sort of standard definition of a climate projection. which is a potential future evolution of climate variables, parameters, I would say almost always computed with the aid of climate models. And one major difference from predictions is that the projections are conditional on a number of assumptions that have to be made concerning, in particular, future socioeconomic and technological developments. So relating to the energy systems, energy policy, population, land use, and so on. So we're exploring a world of different possible scenarios, all of which might be equally possible. The particular scenarios of greenhouse gases that we use are called, referred to as representative concentration pathways, or RCPs. And these, for example, form the basis of the most recent Intergovernmental Panel on Climate Change Fifth Assessment Report. So at the top we can see 4 of the most commonly used RCPs, expressed here in terms of their radiative forcing from 1850 out to 2300, though we're mainly interested in out to 2100 here. So you can see the highest of these is RCP 8.5, which is named after the radiative forcing level it reaches at 2100. So this is a high emissions, business as usual type of scenario, compared with this bottom one, RCP 2.6, in which emissions begin to drop off and end up with a global climate change that's consistent with the 2 degrees target of the 2015 Paris Agreement. I'll also be talking about RCP 4.5, this sort of scenario here, which is low to moderate in terms of its emissions. At the bottom, we can see the projected temperature changes associated with each of these scenarios, which come from a multi-model ensemble of global climate models. So as well as clearly seeing the difference between RCPs, you can also see these shaded areas around the ensemble average. And this is showing the uncertainty range, the intermodal range for each of the RCPs. And you can see that it's quite large and gets larger as we go further into the future. So in this figure, we can essentially see 2 of the major sources of uncertainty associated with climate projections. So one is the emissions scenario, the greenhouse gas forcing. The second major one is differences in model structure in response to that forcing. What you can't really see here is the third element of uncertainty, which relates to the natural variability of climate. Now the results, the projections I showed you on the previous page all come from global climate models, which have a relatively coarse spatial resolution. Each grid box is a few hundreds of kilometers. So for ECEM, we use dynamical downscaling to try and gain some added value by going to higher spatial resolution. So in dynamical downscaling, a regional climate model over a smaller domain is nested within the GCM, and the sort of boundary conditions, circulation and so on are used to force the regional climate model. So downscaling itself is also a source of uncertainty. So again, it's important to use a multi-model ensemble. So different regional climate models, RCMs, driven by different GCMs. The ensemble we use comes from a major international project initiative called Cordex, and in particular Eurocordex. So this is the Eurocordex domain here. And the simulations from Eurocordex have a grid box resolution of 12 kilometers, forced by a range of the CMIP5 global models, so the models we were looking at on the previous slide. So we're taking advantage of the potential benefits of high spatial resolution, but because of the simulations that were performed in Cordex, it means that we're restricted to looking at 2 of the RCPs, RCP 8.5 and 4.5. Now, ECEM is one of 2 Copernicus C3S projects that are currently focused on the energy sector. The other one is CLIM for Energy. And so we've taken advantage of some of the work that's been done by our sister project, CLIM for Energy, and taken some of the process climate RCM data that they've produced. So CLIM for Energy have tended to focus more on the climate projections, whereas ECEM has, as Phil Jones explained to you, has done a lot of work on the historical data. So CLIM for Energy took the view that for many users, and particularly where the projection data is being run through complex impact models, it's not possible to use a very large ensemble. So from the Eurocordex ensemble, they selected a number of smaller ensembles of 3, 5 and 7 members. In ECEM we're using the 7-member ensemble. And the ensemble was, the sub-ensemble was selected by considering how well the models are producing compared with observations, thinking about the sensitivity of the underlying global climate models, and thinking about the range of climate responses in the regional models, and combined all that information to select, for example, the 7-member ensemble. And this includes, well, it's a combination of 6 different RCMs and 5 different driving GCMs. And again, these are the variables that CLIM for Energy looked at, and you can see that they coincide nicely with the variables that both the Phils were talking about as the focus of ECEM. CLIM for Energy also undertook some bias adjustment of most of the variables. They used the WFDI gridded observed data set that Phil Jones talked about, but a slightly different adjustment method to the one that was used by us for the historical data. So this is a cumulative distribution function transform. Essentially, it's a quantile mapping method. And the advantage of this for applying to the projections is that it accounts for nonlinear changes in the distributions as you go from current to future climate. Having done the adjustments, CLIM for Energy then assessed how the improvement in a similar way as Phil Jones talked about for historical. And there the comparison was done with station data. So here's just one example of the CLIM for Energy results. You can see the full kind of report on what they did kind of here, which is publicly available. So this example is for winter precipitation, looking at biases both in mean precipitation but also various aspects of extremes. Forget the middle column, but just look at the difference in biases between the right-hand column, which is the original unadjusted data, and here the adjusted data, and you can see that in all cases the biases are reducing. So, okay, but one caveat I need to kind of make now is that on these climate change projection timescales, we're essentially talking about unverifiable timescales. So we refer to the good reproduction of observations by the models as being a necessary but not a sufficient guide to the reliability of future projections. If the models miss a feedback process, for example, that's important in future climate, then the projections won't necessarily be reliable. Okay, so we took the climate projection data from CLIM for Energy, did a bit more processing to get it into country and cluster averages for inclusion in the demonstrator. And the demonstrator is an online tool that allows you to download and visualize climate data and energy data as well. So here's just a reminder of the variables that we looked at, the names of the 7 different models that we used, and an indication of the availability. In some cases it wasn't possible to bias adjust particular parameters. Some cases parameters were missing from the models, and we decided not to include snow depth in the demonstrator itself because of concerns about variability. But all the information about the processing of the data, both by Clim4Energy and ECEM, is documented in variable fact sheets and other guidance material on the demonstrator. So now, finally, let's have a quick look at some of the projections themselves. And this is an example of the types of maps that, that can be produced. And here we're looking at global horizontal irradiance, GHI, for the high emissions scenario, RCP 8.5. This is the ensemble average, so the average of 7 models. And we're looking at long-term means, 30-year long-term means. So here for 1981 to 2010 for spring, and here on the right-hand side, the 30 years centered on 2050. If you look carefully at Southern Europe, you will see that as you go to the future, things become kind of a bit redder, darker red, showing us that irradiance is increasing as you go into the future, as you might expect. But if we look in Scandinavia, if you look closely, you'll see that the colours are a bit paler, indicating a decrease in irradiance, and that's related to an increase in precipitation, and associated with that an increase in cloud cover. So as well as being able to plot maps in the demonstrator, you can also plot time series. And this is an example of what we call a full projection plot. And we spent quite a bit of time thinking about how best to display this information to give a sort of good indication of uncertainty, but also to be able to identify robust changes in the projections. This is all documented on the demonstrator, so I'll just go through fairly quickly. But what we're looking at here is the ensemble mean for RCP 8.5 and for RCP 4.5. So I should say this is summer temperature for France. You can see the individual models, which are the thinner lines, and then the max-min range for each time step across the model shaded to give us an indication of the intermodal range. We've also shown 2 different sets of observations, both of which Phil Jones talked about, so adjusted era interim and WFDI. I could probably spend another 10 minutes talking about this plot, but I'm not going to do that. But just to say, as you go into the future, you can sort of see that the sort of trends really begin to emerge, and by the end, in the second half of the century, we see this sort of big emerging difference between the high and the lower emissions scenario. Okay, for temperature, Europe tends to warm pretty consistently. If we look at precipitation, then we see contrasting seasonal and spatial changes. So here, for example, this is winter precipitation for Sweden, and we can see some indication of a slight increase in precipitation as we go into the future, whereas for summer precipitation in Spain, we're seeing more of a decreasing trend. But there are some variables where we don't see so much of a change, and now here we're looking at wind speed. This is annual wind speed for Germany, and you can see that there's really no trend evident here at all. But the most striking thing about this graph is this difference between the WFDI data in red to which the model ensemble was adjusted, so you can see it agrees quite well, and the adjusted era interim data, which you can see show substantially lower wind speeds than WFDI. So this takes us back to some of the issues and the discrepancies that Phil Jones talked about at the beginning. So this issue associated with what observed data you use to bias adjust both historical data and projections is, I would say, still a kind of major uncertainty where more work is needed. And so there are clearly data issues here. There are also data issues associated with this first point, and in some cases we don't have suitable observations for bias adjusting projections. The ensemble size that we've used for the climate projections is relatively small, so unlike Phil Betts, we can't show probabilistic information, which is why we showed the max-min range. For the future, it would be quite nice to include the lower RCP 2.6 projections. And one area where we'd be particularly interested in getting feedback from you is to do with some of the visualizations of the data. So particularly those full projection plots that we show, are they kind of too complex, or do they give an appropriate representation of uncertainty that's useful for you? So finally, my last slide, which summarizes what's available in terms of climate projections currently in the demonstrator. So information at the country scale, also slightly higher resolution cluster scale, so 100 subregions across Europe. The projections run from 1979 to 2100, covering both the historical forcing and the RCP forcing period. As I said, these are based on 7 models with an original resolution of 12 kilometers, with bias adjustment in many cases, encompassing energy relevant variables, so radiation and wind speed, as well as more standard variables like temperature, precipitation. We have various combinations of the different ways in which data are presented on different time scales. So the highest temporal resolution information is daily, but we also have information at monthly, seasonal, annual time scales, absolute values, in some cases anomalies and long-term means, and max-min ranges. And as you saw from the examples, you can visualize the data both in map form, also as time series, including the full projection plots. Okay, I can see Alberto is asking me to wrap up. So that's my last point, and that's a bit of a teaser for a future webinar. So thank you.
Okay, thank you very much, Claire. That was also a very interesting and informative overview of the climate projections work. Of course, there's much more available on the ECEM demonstrator that has been mentioned a few times during the presentations. You should already have the link, but I will give you the link also in the next slides. Before we go there, as we said, we are going to answer some of the questions. We are at the hour now, so if people need to leave, by all means, feel free to leave. And as I said, this webinar is recorded, so you can come back and answer and listen to the answers if you wish later. Otherwise, we'll keep going for a little while, maybe 5–10 minutes over. We got 3 questions here, so I'd like to ask Phil Bett to answer the first question, please, about the skill and in the interannual variability in the trended data. Over to you, Phil, please.
Yeah, hi. That's a really interesting question. We have looked at the detrended skill. I hadn't really thought of it as being super important to users, so it's really useful information to know that it would be relevant to users in making these sort of decisions. So we've got that, and hopefully we can look to making those results available and looking at them in more detail in future.
Okay, thank you, Phil. And there is one question here that perhaps Claire can have a go at if you wish, otherwise I can try. Personally, I am not entirely sure I fully understand the question, but we can try to address it. Claire, would you like to have a go? Or?
So is that the question about the number 2?
Yes.
Well, we do also have, so in terms of the historical climate information and the projections, some of that information is also available at the cluster scale, which is slightly finer than the country scale. I mean, of course, in terms of impact, there will also be consistent energy variables, and those will be talked about in a future webinar. There's currently already historical energy information available in the demonstrator. I mean, we're very conscious that this issue of spatial scale always comes up, and it's something kind of for the future. But it's important to realise that we need not just model data, but also the observations, and sourcing those at suitable scale can often be a sticking point.
Okay, thank you very much, Claire. And maybe the next one is also for you, if you'd like to give maybe a short answer to this one.
Okay, well, maybe the first part is for you, but I mean, the CMIP6 projections, they are currently being the global modelling groups are currently starting to run the global simulations, and those won't be available within the ECEM timeframe. I mean, I think they will begin to become available probably towards the end of next year, but more coming in 2019. And of course, there will be a delay before the nested regional climate model simulations can be run. And maybe you can just comment on the sustainability of the demonstrator and the general ECEM activities.
Yes, excellent. Thank you, Claire. So we actually forgot to mention the timescale of ECEM because we are getting close to the end of the project now. It's been a 27. It was initially 27-month project, and we have 3 months left now. It's going to end at the end of January, and so there may be a little extension, but then that's about the time that ECEM will finish, and the demonstrator has been developed as much as we could, but we've received a lot of positive feedback about it, and so there is very strong willingness to continue with this work and to keep the demonstrator going. And so please stay tuned and provide your feedback. And this is also what we are asking you with this next slide. So here is the address of the ECEM demonstrator, ECEM Climate Copernicus.eu/demo. And also want to bring to your attention other 2 webinars that have been scheduled. I mentioned at the beginning there's going to be another one on energy. This is happening during November. We'll advise on the exact date very shortly. And then there will be another one again on the demonstrator. We had one last month, but there's going to be another one because we are in intense phase of development right now for the ECEM demonstrator. So there's much more data coming in, particularly on the projection side and the energy, energy projections particularly, but also seasonal. and this will be presented sometime in December. There's also going to be a stakeholder workshop in sometime between December or January perhaps, but this is need to be also decided still. Again, watch this space at the ECEM project website or getting in touch with us. There is also a feedback form to be filled out in the ECEM demonstrator website, and we'll look forward to your continued interest and feedback as we move on. And I'd like to thank again all the presenters for their great presentations. These will be available online soon. And of course, I'd like to thank the partners of the project that are listed at the bottom here, as well as the collaboration with the World Energy Meteorology Council, and of course the support and the contributions from the Copernicus Climate Change Service Program, which is the overarching program where ECEM sits. So thank you very much again for your participation, and good night, good morning, or good afternoon, wherever you are. Thanks again. Bye-bye now.